Okie dokie, here we go. 9, 1 inverse functions. So we are jumping around the book on this one. 2, 3 was yesterday, and we are not going to do chapter 2, 4, but we are going to, in its place, do 9, 1, because for some reason the book does direct variation on 2, 3, and then doesn't have inverse variation right after it. So we're going to slot that one in. So here's what we're going to learn. We're going to learn how to use it. And then there's also, we're going to learn how to use combined variation. So what if we want to be direct and inverse, or we'll throw in some exponents and things on there too. Okay? So there's a word problem on example 3 talking about the lifespans of mammals on here. So a couple new vocabulary phrases for us. Inverse variation, which is going to be the opposite of direct variation. We'll deal with that next. We'll deal with that first. And then once we have that, we'll knock out combined variation. Alright, so first things first. So we already know that direct variation, we have a formula for it, and that is y equals kx. Right? That's direct variation. Put it out here so we can see it. Direct, y equals kx. And so inverse variation. On direct variation, it was something times x. Now it's x is being divided by something. All right? X divided by k would be an inverse variation problem. All right? So let me get rid of that writing so we can take a look at this. Right? So here's an example of inverse variation. So take a look at this as our rate over here. As our rate increases, the amount of time that it takes decreases. And that makes sense. The faster you run, the less time it's going to take to complete a race, something like that. Right? So it's inverse. So a couple things that need to happen. As we get bigger over here, we're going to get smaller in the other formula. All right? So it has to have that situation going on for inverse variation. And also, as we multiply across, now we're going to get the same things. Right? Whereas direct variation, here's an example of direct variation, 3, 6, 9 turned into 6, 12, 18. For this one, the jump we had to be multiplying by 2 was the same. Now if we multiply them, we'll always get the same number all the way down the column. All right, so that's how we can tell. All right, so we already know how to do this with direct variation. Let's learn how to do it with inverse variation. So x and y vary inversely. So we've got y equals x over k. And so we can plug in some numbers. -5 equals x over k. Sorry, got to plug in my x number. 3 over k. I'm going to multiply this up. -5, k equals 3. I'm sorry. I flipped it over. Go back into your notes. I put down the wrong thing. It's not x over k, it's k over x. K over x. K over x. Sorry about that. I got ahead of myself. I knew that didn't look right. -5 equals k over x. As soon as I started writing the 3 on top, that didn't look right at all. All right, so now here we go. We're going to times it by 3 on both sides. -5 times 3. We get -15 for k. Write the function. We're going to jump back in here and we're going to say y equals -15 over x. Scratch this out. K over x. X on the bottom. -15 over x. All right? All right, so get that straight with the good formula, not the bad one I gave you first, and see if you can do understanding check number 1. All right, second part, see if we can look at these tables and see if it's direct or inverse. All right? So the test for direct is, can we multiply straight across and get the same, get an answer by multiplying by the same thing every time. So 0.5 times 3 gets us 1.5. Is 2 times 3 6? Yes. Is 6 times 3 18? Yes. So this is direct variation. Okay, because we had to times by 3. Let's check the next one. 0.2 times something to get to 12. Not sure, but I know 2 times 6 is 12, so this would be times 60. All right? Is 0.6 times 64? I'm not sure, but I know 6 times 6 is going to give me 36, so it can't be 4, so it is not direct. Let's get that out of here. So now let's try multiplying straight down. 2 times 12 is 24, so 0.2 times 12 is 2.4. 6 times 4 is 24, so we're on to something here. 1.2 times 2, that's also 2.4. Yep, we got a winner. Inverse variation. All right, we multiply straight down, we get the same thing. Let's check this one. All right, so here we know this could only be inverse. And here's how I know that. Because as we get bigger here, 1, 2, 3, we get smaller here. So that can only be inverse variation. Let's check to see if it actually is. What's 1 times 2? 2. What's 2 times 1? 2. Looking pretty good. What's half of 3? 1.5. Oh, nope, it falls apart. So this is neither. All right, neither direct nor inverse variation for the third one. All right, so it does say write functions to model if we get a direct or inverse variation. So we'll go back up here. For this one, it's y equals, what do we have to multiply by? 3, so y equals 3x. And for this one, we're going to say y equals k over x. And on this one, 2.4. The thing we get, 2.4 divided by x gets us our y number. All right, so our k in this situation equals the bottom number, what we're multiplying to. See if you can figure out understanding check number 2. All right, so let's do our real-world connection. Heart rates and lifespans of most mammals are inversely related. All right, the higher your heart rate, the lower your lifespan's going to be, right? If you're nice and calm, low heart rate, you're going to live forever, right? If you're a crazy person and your heart is beating 1,000,000 times a minute, it doesn't look good for you in the long run. All right, so that's what's going on here. Use the data to write a function that models this inverse variation, and use your function to estimate the average lifespan of a cat with a heart rate of 126 beats per minute. All right, so we have our direct variation here, so let me bring up our calculator. We're going to need that. Let me get rid of, oh, thought I would get rid of it. There we go. Okay, so we want to multiply across here. So 634 times 1, 5, 7, 6, 8, 100. We get this number here. Let's check the next one. 158 times 6307 200. And we get something like that. So pretty close, right? Not exactly the same. It's a real world situation. The numbers aren't going to be perfect, but pretty close. Let me finish it up by doing the last two. 76 times 13,140,000. And 63 times 15,768,000. And those are in minutes, so that'll be a lot of years to live, but that's how many minutes. So 99, 99, 99 all the way across. So what would be our best guess for K here? Something like maybe, and what are we in here? Thousands, so this is in millions. Maybe 995 million, best guess. Right, so let's go ahead and put that in for our K. 995 million. Right, we're just trying to approximate here. So if that's our K, we're going to say Y equals 995 million over X. And so let's go ahead and figure out what that would be. The lifespan of a cat with a heart rate of 126 beats per minute. Careful here, the tendency is to put that in for X or Y. Which one's it going to be? Make sure we have X and Y here, so heartbeats is going to go in for X. So Y equals 995 million over 126. Okay, let's plug that in. Calculator. 995, 1, 2, 3, 4, 5, 6 for a million divided by, and what was our number for the cat? 126. So 78, is it million? Nope, 7,896,825. Let's see if that makes sense. 126 would go right in between here. Is 7 almost 8 million, somewhere in between 6 and 13 million? Yes, it is. So story checks out. We'll go with that. All right. See if you can do the same type of thinking on number 3. And you're going to use the chart here to answer your understanding check on 3. All right, so now let's move on to the second objective, combined variation. So we've done direct variation, right? And so that's our formula here. But now with the square of x, not just directly with x. So that means it's the same formula, but we'll put a 2 on right here for the exponent, right? Inversely looks exactly the same, but what if we said with the cube of x cubed? So then we put a cube on the x down here. Now here's our new thing, joint variation. Okay? That means that we're going to have direct variation, same normal formula, kx and y, right? So we have a double multiplier here. So a couple different options here. Combined variation is just a combination of direct and inverse variations. All right? Complicated relationships. Not super complicated, but more complicated. All right, and so here's one where we're jointly with x and y. So x and y are going to be with the k, and then divided by, inversely, we throw it on the bottom. All right, so a couple different options. So let's take a look at an example problem. Newton's law of universal gravitation is modeled by our formula here, g mass 1 mass 2 over distance squared. Right? F is the gravitational force between two objects. G is gravitational constant. Describe Newton's law as combined variation. So we want to put this in words, right? So what we're going to say here is gravitational force, that's F, is, right? So that's our equal sign. Is gets us to the equal sign. And now, so on top here, G is a constant. So this is kind of like saying K, X, Y. Okay? So this we would say is jointly proportional. We're going to use proportional. Let me just check. I think that's the phrases we want. Is jointly variable. All right, so sorry, we'll use variable. Proportional is in a different one. Varies jointly. We can say it like that. Jointly proportional, meaning the same thing. But we didn't introduce that vocabulary, so I won't throw it in there. Varies jointly with M1 and M2, and inversely, so now we're on the bottom, with the square of D. With the square of the distance. Now the only thing that we don't put in here is this big G up here. How come we don't talk about that? Because that's the constant, right? That's like the K. And in our statements here, when we look back at our chart, notice that y varies directly with the square of x. We don't talk about the K at all. The K is in there with varies. The varies implies we're going to have some constant in there multiplying it. So in this case, as soon as we say varies up here, we're implying that we've got the constant, which in this case is the large G. All right, a lot going on there, but see if you can make heads or tails of example 4. All right, so let's find a formula here. The volume of a regular tetrahedron varies directly as the cube of the length of an edge. The volume of a regular tetrahedron with edge length of 3, is 9 root 2 over 4. Find the formula for the volume of a regular tetrahedron. So let's go back in here. The volume, so I'm going to write as I read. Volume varies directly, so K, with the cube of the length of an edge. So length cubed, okay? And so if they tell me the volume is 9 root 2 over 4 when the length is 3, let's jump in there and figure out what the K is, okay? So the cube root of 3 is 27. 9 root 2 over 4 equals 27K. And so we'll divide by 27. And so dividing by 27, it's going to end up in my denominator there, so I'm just going to put it right down there. And so 27 times 4 is 80 plus 28, which is 108. 9 root 2 over 108 equals k. And does 9 go into 108? 9 times 9 is, or 9 times 10 is 90. 99, 108, yes it does, 12. Forgetting my times tables. So root 2 over 12 equals k. And so we can punch that back in for our final formula. B equals root 2 L cubed all over 12. And there you go. See if you can do the same thing for understanding check 5. And there she is. That's the last thing. So any questions, make sure we cover it in class. Otherwise, have a good weekend, and we'll see you next week.